Yes, thank you for the invitation. Welcome back from the coffee break. I took the liberty to change the title. The content remains the same. We'll keep it informal, so if you have questions, feel free to scream in the middle of the talk. Okay. This talk will be about how to train neural networks. So we are talking, Praneet laid out a very nice foundation for what optimization looks like, optimization theory looks like. This talk will be kind of using these ideas to come up with better ways to train neural networks. Better being, can you train them faster? And can you make them work better on new data? Can you make them generalize better? So these are the two kinds of notions that we're interested in, faster and better generalization. Am I audible at the back? Okay, so for the purposes of this talk, neural networks are very simple objects. You pump in an image from the left-hand side. You apply some operations on this image. This could be convolutions. This could be matrix multiplications. These are called fully connected layers. Pooling is another operator that people tend to use. All said and done, these are nested applications of some operations on the same image. You keep doing this a few times. This is what is called a deep neural network, as opposed to a neural network that would be in the 90s, which would be much fewer operations like this. And on the right-hand side, you will get a probability vector. It is a vector. We like to think of it as a probability vector after normalizing it. And what does this vector signify? It signifies how likely this image is to be that of a cat, a dog, a plane, a boat, etc. Training a neural network involves taking a bunch of data like this, images of cars and planes that someone somewhere annotated for you. Someone wrote down what the ground truth object in each of these images is. This is called supervised learning. And then training the network to make predictions on such data. What do? We'll write down a loss function called f of x. F of x, in this case, in machine learning, would represent how much your model differs from your ground truth annotations. Your model is, the job of your model is to predict your ground truth annotations as well as possible, and f of x simply measures the discrepancy between them. X is what I'll use often in this talk. X denotes the weights of a neural network. This is exactly the same X that Praneet was using, the variable of optimization, and you are interested in finding the best such weights, okay? This is not an easy problem for many reasons. One being you would like to understand lots of data, so you'd like to capture variability about lots of data. So I'd like to think of the number of images that I'm interested in of the order of millions. Now, if I give you a lot of images, the function that you're fitting on these images also needs to be complicated enough, right? Otherwise, simple functions are not going to do well for complicated data. So f of x is also a rich function. It is typically a non-convex function in its parameters. So this optimization problem, benign though it looks when I write it down like this is a high dimensional non-convex large scale problem, optimization problem, and that is what makes solving this hard. Okay, it is not new, but there is a very, very simple algorithm that people typically use to solve these problems. And this algorithm is called stochastic gradient descent. It is different from gradient descent in the following way. So xk plus 1, it is the same as xt plus 1 that you had in the previous lecture, is given by xk minus some step size, eta, this is the same eta that we saw in the previous lecture, times the gradient of f of xk, counted not over all your data, but only over a subset of the data. I have a million images. It doesn't make a lot of sense to evaluate the gradient of my loss function on all these images if I don't know what step size I should be picking optimally. So I take a subset of my images, let us call them B, B images out of 1 million, and this is what is called a mini batch. So stochastic gradient descent is stochastic because you're not evaluating the gradient completely on your data set. You're only evaluating it on a subset of data, the mini batches. And you keep doing this forever, and then at the end of the day, let's say after you get bored, you write down your weights on your hard disk, and that is a neural network that you would use in practice. Okay, among the simplest algorithms you can write down. First order optimization, nothing spectacular going on, and yet so this was invented in, let's say, 1951 in the stochastic optimization literature. And as you can imagine, by now there are many, many, many variants, right? This is also among the slowest algorithms you can cook up for first order training. There are things that are called AdaGrad, RMS prop, Adam, some of you might know. or SAG, SVRG, Datasha, Katyusha, and all of them. And these are, every single one of these algorithms is faster than SGD on paper. And yet, when you see what people use in practice, so this is a picture. The x-axis is the number of operations that you perform when you do a forward pass to the network, how big the network is, roughly speaking. The y-axis is how much accuracy this network gives you on a typical data set that people like to think about in this world called ImageNet. This is a large data set, so people think it's a good benchmark data set for doing supervised deep learning. And as you keep fighting for numbers, as you keep discovering newer and newer neural networks, you get like all these circles. Every one of these points, well-performing networks they are, was trained with one algorithm, and that is SGD. These algorithms, which are faster on paper, they do not work so well for doing machine learning. Why? We don't really know. And that will be the question that we are interested in answering in this talk. What is in these simple updates that is so special for machine learning? From an optimization perspective, it is a bad algorithm. There is no question about it. But for a machine learning perspective, it seems to be particularly useful. And that is what we are going to understand this time. Okay? Here is one insight into what SGD might be doing. I did an experiment. I took a convolutional neural network on a data set called MNIST. MNIST is a data set of digits from 0 to 9. And your job is to take one of these images and then classify this image as being that of a 3 or a 4 or a 5. You take a network, you train it for some time, and after training is finished, roughly speaking, the error has plateaued out. I'm evaluating the Hessian of my loss function at that location. The Hessian is a matrix, number of parameters times number of parameters, and that tells you something about the curvature of the function locally, right? This is a large matrix, so this network had about 50,000 weights. So it's a matrix of 50,000 times 50,000 entries. And what I'm plotting here is a histogram of the eigenvalues of the Hessian. So it is the eigenspectrum of the Hessian. Yes. There is no end per se, so you basically just stop somewhere. Yeah, exactly. And what you'll immediately notice is that out of these, so this is two different independent runs, and I'm just overlaying them one on top of each other. So many eigenvalues are essentially zero. Almost 95% eigenvalues at the end of typical training run are zero. And what that essentially means is that if I stand at this location in the energy landscape, no matter which direction I look at, the loss function is locally flat. This is a local phenomenon, it is locally flat. There are, of course, a few eigenvalues that are large. These typically are the batch normalization eigenvalues. And these are all the directions in which the loss function increases sharply. They're positive eigenvalues. So there are directions in which the loss function increases sharply. Most of the directions are such that the loss function is locally flat. If you kind of zoom in near the origin, you'll see that there are some negative eigenvalues, not too many of them. So this is not a local minimum. It is really a saddle point. There are both positive eigenvalues, there are both negative eigenvalues. But the most drastic point about this picture is that there are so many eigenvalues that are zero. And this point remains consistent no matter what network I train, no matter what data set I use, be it text, images, be it an LSTM, be it a convolutional neural network, train it with SGD or train it with a slightly different variant of SGD, let's say Adam, there is a very large proportion of eigenvalues which is essentially zero. Larger the proportion of zero eigenvalues, the better the networks tend to generalize, is what we saw in experiments. And now you know something that optimization theory did not tell you, right? You ran SGD on your function, and you found a place which is essentially flat. Now you can play a simple game. So I know that SGD works well. I know that it finds such kinds of flat regions in the energy landscape. So I'm going to go looking for them beforehand. I'm going to construct a loss function that artificially puts more importance on regions which are flat. The idea being that instead of letting SGD find these regions by whatever magic it concocts, I can do it more explicitly, okay? So here is how one would do it. You write down your original problem, the same thing, x star equals argmin of f of x. Rewrite that as argmax of e to the negative f of x. You haven't done anything yet. In fact, if f of x was a nasty function, you exponentiated a nasty function, you made it even worse. Okay? You're going to take this modified loss function and then we are going to smooth this. So G sub gamma is a Gaussian of variance gamma. And you're convolving your loss function e to the negative f of x with this Gaussian. Smoothing smooths a loss function. This is smoothing by a Gaussian kernel. You put in a log there to bring back the scale, but at all said and done, you're taking your loss function and you're smoothing it in a special way using a Gaussian. This is what a physicist will recognize as a local estimate of the log partition function. If G sub gamma was identity, then you would be computing the entire partition function. So we call it local entropy or local free energy. This is not that different from f of x. It's just a different loss function. So instead of using cross entropy loss to train your network, you are going to use this new loss function to train your network. Evaluating the gradient of this function is slightly more complicated than backpropagation. You have to do Markov chain Monte Carlo updates, so what is called longevity dynamics, but you can do it. And here is how it looks. So focus on the left-hand side picture. So this is a data set called CIFAR 10, which is like 10 classes, cats, dogs, planes, boats, horses, frogs, etc. The black line is a typical training curve obtained by stochastic gradient descent. The x-axis is the number of weight updates that you make, the xt of the xt plus 1, xt plus 1 equal to xt minus the gradient. And the red line is the validation error of this algorithm called Entropy-SGD, which is minimizing the loss function that we just cooked up, local entropy. Yes. Exactly, yes, yeah. And so that is very nice intuition. You will see it in a couple of slides, how it relates to the Laplacian. Local entropy minimizes a smoother loss function than the original loss function. Smoother loss functions are good. We expect it to be faster, simple. What is also surprising is that it typically also tends to give you good generalization errors. So not only is it about, let's say, 40% faster, give or take, it also gives you better generalization error. And this effect persists across architectures, across data sets that we have tried. This really means that you started out by building upon this intuition that I want to improve SGD. By looking at some property of SGD, you cooked up a loss function. You try to run an algorithm to minimize this loss function, and voila, it works. Why does it work? We don't know yet, right? So let me give you one insight from some models. Yes. We cooked up a smoother loss function, and we know mathematically that this should be faster. Why should it have better generalization? We don't know. Better generalization performance. So why should it work well on new data is something that we don't know yet. But here is one insight from statistical physics to answer that question. And here is how it goes. So there are models that are called binary perceptrons. So binary perceptron is a single layer neural network. The data that you feed to a binary perceptron is +1, -1 inputs. So all the pixels of your image are +1, -1. The weights are also +1, -1, and so are the labels. So it's a binary classification problem with discrete synapses. It's a very hard problem. So it's a prototypical hard combinator optimization problem. And the physicists have invented methods to analyze how the loss function for a binary perceptron looks like. And let's kind of dig deeper into, this is a cartoon from these results and calculations. So inside the circle, every single point is a perceptron, okay? The red dots are all perceptrons that have 0 training error on a given data set. So I create a teacher, I create a data set that the teacher labels for me, and then I look at how many students have 0 training error on the data set that is created by this teacher. The red points all have 0 training error. And there are exponentially many of these red points. There are very regions of high energy in between these red points. So finding these red points in this large high dimensional Hamming space is hard. The distance between 2 red points scales linearly with the dimensionality of the problem. Although there are exponentially many solutions, it's very hard to find a solution. Standard thing about combinator optimization, more or less. What they also discovered is that in addition to these isolated solutions, which you might intuitively imagine as sharp locations in the energy landscape. There are few locations, very few of them, in fact, a constant number of such clusters that are these blue clusters. Inside this blue cluster, this is a very, very tiny part of the parameter space where every single configuration of the perceptron weights has zero training error. So imagine yourself in this large room, and then imagine something that is like as big as this. Every single configuration inside this small volume fits your training set perfectly. And there are lots and lots of isolated solutions everywhere else. Finding such a small region in this large space is very hard. But you want to find them. Why? Because you can show that this region gives you better generalization. It gives you better generalization because generalization at the end of the day is measuring the performance on perturbed data. If you have a one-layer neural network, then perturbing the data is equivalent to perturbing the weights. If you are stable with respect to perturbations of your weights, then you're also expecting good generalization data. So intuitively, yes.
You're saying they are wide in the sense you said before, the spectrum of the Hessian has a lot of zero eigenvalues.
Yes. Yeah, so the Hessian and this are slightly different objects because the Hessian is a very, very local object, whereas this is still a non-local object, right? So you should think of wide. So wide for me means a large volume of a sub-epsilon level set. The Hessian is different from this. The Hessian is simply a motivational experiment, so speaking. There is no Hessian, exactly. This is a completely discrete space, so all you can measure is volumes. Yes.
So you said that smoothing is very good using this Gaussian kernel, for instance. What happens if you increase the batch size? Because you have also some noise which is due to the fact that batch sizes are typically very small.
Yes.
And so you have these two effects. You can smooth explicitly with your approach, but you can also increase batch size. How
Yeah.
does this differentiate?
Yeah, so two answers to that question. Increasing the batch size does not lead to acceleration according to optimization theory. So you should not be any faster because it takes more time to compute the gradient on the batch sizes. So even if you make fewer updates, this we know from optimization theory. In neural networks, typically people have come up with interesting ways of scaling the learning rate and the batch size, scaling eta and b. We will talk about that in a few minutes. Smoothing is something that you do on the loss function. Increasing the batch size is something that you do on the optimizer. They are two totally distinct things, right?
In fact, you replace your
Or,
function by either a smooth version or by a surrogate which is obtained on a small batch size. You can also say that at each iteration you change your function
yes.
by some.
Yes.
So it's also changing.
It is changing the local dynamics of the algorithm. But if I wanted to be very strict in how I define the function and the algorithm, then I would say that changing the function is a thing, changing the algorithm is something else. And we'll kind of dig deeper into this in a tiny bit. Okay, so some moral of the story is for this hard problem, you want to find dense regions. Dense regions are hard to find because there are so few of them. And SGD manages to find them. That is the surprising fact. So after being initialized somewhere here, SGD manages to reach a region that it shouldn't really be reaching. The physicists would think of this as tilting the Gibbs distribution. The Gibbs distribution is the distribution that puts probability mass on all the solutions. In this case, the Gibbs distribution does not differentiate between the red points and the blue points. They both have the same energy. They're both at the ground state. In fact, because the red points are dominant with respect to the blue points, the Gibbs distribution does not even see the blue points. The only way of finding this blue cluster is for you to tilt the Gibbs distribution and discover kind of these large deviations phenomenon, and which SGD seems to be doing, and which is what we'll dig deeper into very soon. SGD also, right? Because entropy SGD just does it better, but SGD also does it. Yes, there was a question.
So when you say dense regions, are all the weights, are they close in like having space? Is that what you mean?
Yes. Yes. So in fact, like by close, a vanishingly small fraction of your neighbors is not a solution.
So SGD finds them in decently short time.
Yes, 100 epochs, 2 hours.
So all the rate points have zero training error, right?
Mm-hmm.
So they are equal in terms of generalization guarantees. So
No, so they have zero training error. They may have different validation error. The yes.
But when you generalize, you only look at the training error, right?
No, the opposite. So you only look at the validation error. So good generalization means good a small gap between your training error and your validation error.
And how blue point is different from the red point?
Uh, in the training error, there is no difference. The blue points only have many neighbors which are also solutions. That is the so there is no solution in the neighborhood of the red point. There are many solutions in the neighborhood of the blue points.
So if generalization means you take a different sample, you take a different randomness of the landscape here, and then you say the red points will be somewhere else, but the blue will be in the same place.
No. So generalization means you take a different data set.
Yeah.
In
data set is what defines the randomness of the landscape.
the landscape is averaged over the data set. So this is a replica calculation, right? So you average over the data set, and this is the landscape for one teacher. The teacher is fixed. Data sets are created. You take an average over the data sets, and then you draw all the other students. Does that make sense?
But you have a loss function, and you have the xi, the data,
Hmm?
and you train.
Hmm?
This xi is defined the randomness.
The xi is defined. Yes.
Then you take a new data set,
Hmm?
xi prime, if you want.
Yeah. Yeah.
It's a new randomness.
Hmm?
It's a new.
Yes, but we can that is the standard machine learning setup. In this cartoon, what we are interested in is finding how many students fit the same teacher. So you are taking an average over the data sets created by nature's distribution. It's a yield, exactly. Near the which points? I didn't get the first part. Yes. So if I am a blue point, then my neighbor is also a solution. Yes. Yes. There are the red points are far away from each other, so the red points are also far away from the blue points. The red points are far away from each other. The red points are also far away from the blue points. So it is the distance is scales linearly with the dimensionality of the perceptron. So it's like imagine like little pinheads in this room, and then one of the pinheads is a blue point, and then all the other pinheads are red points. It's kind of it's a nasty place. Constant number of blue clusters. So exponentially many solutions within the cluster, but subdominant, yes. Okay. That tells you at least in one physics model, you know that finding wide regions or discrete wide regions should give you better generalization. This doesn't tell you why it works for neural networks. We don't know that. Here is a slightly complementary perspective. So we'll look at partial differential equations, and what I've written here is the heat equation. I purposely wrote u sub gamma. So u sub gamma is a partial derivative of the function u, which is a function of your weights x, and another scalar parameter that I would like to think of as time. At time equal to 0, u equals your original energy landscape, and as time flows, as time increases, u sub gamma is the Laplacian of u. And this is the heat equation, so it governs the flow of heat in this room, of energy in this room. And not surprisingly, if I start from some loss function f of x and let things diffuse, I smooth out the loss function because of the diffusion, because of the Laplacian. What you can show is the function, the smoother form of the loss function that we said is called local entropy, is a solution of a slightly different partial differential equation. In addition to the Laplacian term, you also have another term which is negative gradient u squared. So you're also using the gradient information to smooth. So Hamilton-Jacobi equations, which is what this equation belongs to, are faster to smooth than heat equations because they use both the Laplacian and the gradient information to smooth. If I start this Hamilton-Jacobi PD with which my loss function as the initial condition and let things go, then at time equal to gamma, I'll get exactly local entropy as my solution. And this is really like a two-line computation called the Kohlhoff transformation, which the PD folks here might know. And but then it's kind of powerful because now I've taken a function that I cooked up from statistical physics or intuition, and I've connected it in a very neat way to a PD. And I can now think of like more interpretations of this. I can connect it back to optimization theory. Okay, and here is one connection. So Hamilton-Jacobi equations are intimately related to optimal control problems. So let's write down an optimal control problem that corresponds to minimizing local entropy. Here is how it goes. So I'm going to write down a stochastic differential equation, and this is a model for SGD. It is not exactly SGD. dx is the incremental update of your weights per infinitesimal time. This is given by the gradient of f. Note that this is the full gradient of f, no longer the stochastic gradient. It is the gradient over the entire data set. And we would like to model the stochastic gradient, right? So you take the gradient over the entire data set and you add some noise to it. In this case, I have added Gaussian noise. So I would like to think of it as stochastic gradient descent equals gradient descent plus some Gaussian noise. It is a model for stochastic gradient descent. I would like to give myself some more freedom. So in addition to simply descending in the direction of steepest descent, I will have a parameter called alpha. And now I'm going to think of how to pick an alpha optimally. And here is how. We like trajectories that descend as much as possible into the energy landscape. So over an expectation over noise and initial conditions perhaps, you want to minimize f of x at time capital T. That's easy. I don't like trajectories which force me to use a lot of control alpha. I would like to use as little alpha as I can. And so you would add another term to the Lagrangian, which is the integral of all the alphas that I've used over this trajectory. And this is, again, a very prototypical calculation that you would do in optimal control. We want to find an alpha that minimizes this cost function across trajectories. The alpha that you come up with is exactly the gradient of u. So alpha star, the optimal alpha that you should pick at each time instant, is the gradient of your Hamilton-Jacobi equation, PD. You will have seen this as the JB PDE, et cetera, et cetera. This gives you a very powerful way of understanding what local entropy does. Instead of doing simply steepest descent at each iteration, it is doing something that depends not only at this location, but a few more locations, because the solution U depends not just locally at X, but it depends on the entire domain, right? The gradient of U is what you are using as the control in your controlled stochastic gradient descent. And you can show that controlled stochastic gradient descent is faster than stochastic gradient descent for finite capital time. And that is why this explains why smoothing the loss function is a good thing to do. Smoothing is good because it lets you converge to the same point faster. Okay. Let's play another game. So I take my Hamilton-Jacobi equation, and I said that both these two terms result in smoothing, right? So let's kill the second term now. You remove the Laplacian, and all you have is what is called the Burger's equation in one dimension. U sub gamma equals -½ gradient U squared. You're only using the gradient information to smooth stuff, no longer the Laplacian. This is a very old equation, and it has very beautiful connections to what are called proximal point algorithms, which Praneet also mentioned briefly as forward Euler in gradient flow. And here is how they look. So this is a cartoon one-dimensional function. The black line is f of x. It is a non-convex loss function that I concocted. The red line is local entropy. As you see, it is a smoother form of f of x. If I were at this location, instead of getting stuck in this location, if I can compute the gradient of the red line, I get a strong gradient that takes me closer to the global minimum. The solution of the non-viscous Hamilton-Jacobi equation is what is given by the blue line here. It is worse than the red line. It is not as smooth as the red line. It has maxima and minima. And yes, these are exactly the shocks. Yeah. So it is decidedly a worse function to minimize. The nice thing is that it still kind of works. And typically what you will notice is the locations of local maxima come down decrease, and the local minima widen in their curvature if you run Hamilton-Jacobi equations. So you can minimize, you can solve this PD, and that will be like doing minimizing a neural network, the loss of a neural network using the non-viscous Hamilton-Jacobi PD. And we'll see how this helps in a tiny way. Minimizing this PD is what is called proximal point iteration, and it goes as follows. So xk plus 1, we said in gradient descent, we wrote it down as xk minus eta times the gradient of f. In this case, I'm going to write it down as an explicit minimization, argmin over all y's of f of y, plus some quadratic force that keeps me closer to xk. This is what is called a proximal operator of f. And as you can see, no matter what gamma I pick, I am a y star that I get from this minimization is always going to be better than xk. So that is why people say that proximal point iteration is good, because it makes monotonic progress no matter what your step size is. And this translates to practice very well because you don't have to worry too much about picking your learning rates. You can pick, this is typically much more stable to learning rates. In fact, it forgets its initial conditions much more quickly than gradient descent. And it's just a much nicer thing to do for neural networks where the learning rates are difficult to tune. Okay. And now that you have made this connection, you get like straight away convergence results and all these things that people have designed for, people have calculated for proximal point iteration. Yes.
It's really interesting. So I want to understand. So you replace your function f, which maybe is terrible landscape.
Yes.
Replace it by this substitution of the Berger's equation.
Yes.
Choosing the time of gamma.
To be something, and then I say that I don't have to worry too much about picking the right gamma. Most gammas work.
So do you have any kind of understanding guarantee that first minimum of this new thing, you replace your landscape?
Yes.
Minimum of this one will be achieved at the same time.
Actually, so for the non-viscous Hamilton-Jacobi, that is a beautiful point. The minimum is the global minimum. So the blue line, as gamma tends to infinity, will be exactly at the global minimum. In fact, and the red line can go anywhere.
The time is very long.
Yes.
Then you have to cross a billion shops.
Exactly. So there is no free lunch. So even though the blue function is nicer to minimize, computing the gradient of the blue function is harder. So the game comes down at the end of the day to evaluating the right-hand side in the argmin properly.
So again, you have to manage the
Exactly.
choice of the gamma, like the step size.
You don't have to manage the choice of gamma, but you need to do something powerful here, more than SGD, to if you want to minimize the right-hand side well.
Because with Berger's, you say computing the gradient is hard, but Berger's there are hypersurfaces where the gradient does not exist.
Yes, yes, yes.
So how do you cross that with the gradient?
You don't. So you typically you only do things locally, right? So you are not going to do this minimization completely. You are going to do what is called an inexact inexact stochastic proximal point iteration. So
it's something that you have hidden.
hidden, yes. So it is more or less a practical thing, and there are certain like convergence results that Stephen Boyd had in some of his older work on inexact stochastic PPI. For neural networks, it doesn't seem to be that bad. I do not know why. Because I believe the loss functions of neural networks are not as nasty as the one that I drew. Okay, so to summarize, cooked up a loss function. I told you, convinced you that this is a good loss function to minimize. We said that it is connected to other standard optimization algorithms. Okay. Let's use it for something practical. So there is some of you might know neural networks are large objects. And if I would like to train a neural network quickly, I would like to use as many computers that I have in my backyard. If I'm Google, I have hundreds of them. So I would like to distribute the training across all these computers. And this is not that easy to do. Why? Because these networks are big. So when you have one network on each computer, you need a lot of communication bandwidth to talk for the two computers to talk to each other. That is what is called the communication bottleneck. If you try to reduce the communication bottleneck, if you make each replica or each computer work on very large mini batches so that they have to talk to each other infrequently, then you get hit by what is called the generalization bottleneck. So you don't get good generalization performance on new data. And the reason why this occurs was kind of a big mystery, and there was a big there's a big push towards resolving this, but this is the fundamental tussle between communication complexity and computational complexity. Here is one solution to fix this, and this is an algorithm that is called elastic-SGD from a few years ago. I'm going to take my n computers, so I have n computers at my disposal. I have my neural network and I put it individually on every computer. So these are just copies of the same neural network that are called replicas. And I'm going to train all of them to minimize their loss. Not independently, they're dependent on each other, and they exactly depend on each other using some quadratic force. It doesn't have to be quadratic, it doesn't have to be exactly this form. You can essentially put any proximal term that ensures that all these different computers, even though they're operating on different mini batches, they try to be close to each other. So it is any which spring force like term. Okay. This is the loss function minimized by elastic SGD. And this works spectacularly well. So for instance, for those of you who are using Android, this is the algorithm that is running on Android for keyboard prediction today. So when you use the keyboard during the day, the first term in black is what is being updated locally on your phone. And when you plug in your phone for charging, the second term is what gets updated on Google servers. So tomorrow morning, you get better predictions from your keyboard because your friend was typing something similar yesterday. And this algorithm works at the scale of Google, millions of keyboards, Android keyboards, even today. Yes, it is a regime called federated learning. It's very impressive, yes. So what you can prove is elastic SGD exactly minimizes local entropy. So I did not talk about distributed training when we cooked up this loss function. Turns out this way of doing distributed training is exactly equivalent to smoothing the loss function, is exactly equivalent to finding these wide regions in the parameter space. And this is nice because until now you cooked up this algorithm using intuition. Now you know what loss function it minimizes exactly. And there are two ways to think about this, right? So if you remember ergodic theory, this is the spatial averaging where I have multiple replicas that kind of travel around the energy landscape, and I'm averaging their predictions or averaging their weights. Local entropy is one loss function. We said it, you can minimize it using Markov chain Monte Carlo. So that is the single particle version of the same loss function. And you can combine the two now. So you can cook up an algorithm which essentially replaces this F here by local entropy. So you can do local entropy twice. Once on one computer and then one more time across all these different computers. It is exactly the same loss function, you're just implementing it differently. Does that make sense? So each computer computes local entropy using Markov chain Monte Carlo, and all the other individual computers compute local entropy again using the distributed averages. And this is an algorithm called Parle. It is a very slight twist on top of elastic SGD, and that works spectacularly well. So again, the black line is stochastic gradient descent for this neural network called wide ResNet. And this is actually a good neural network, so you get errors as small as 4% with SGD. The first epoch of Parle is already better than what you get after finishing the training with SGD. And this is a pretty nice baseline. So what this really means is that you're doing something right that is in tune with your energy landscape. These algorithms can exploit the local properties of the properties of the landscape to come up with good answers. You can also do the following. So all these replicas, they don't have to work on the same data set. They can work on different data sets. So I can take the same data set of 1 million images, and if I have 5 computers, I can split that as 200,000 images each. And because all these replicas are being forced to remain close to each other due to the proximal forces, it doesn't matter whether you did not see image number 1. Because your neighbor saw image number 1, you are going to do well on that image by virtue of being close to your neighbor. So you get this trivial speed up because you are not looking at all the data per se. This is what the second experiment shows. So in this case, each replica, there are 4 replicas, there are 6 replicas, and then each of them is looking only at 25% of your entire data set. And yet you're matching what SGD gets, the black line gets with your algorithm. You can do this for multitask training, you can do this for other data sets, and it works kind of well. Okay. That's, let me skip this. That's the game of a experimentalist, right? So you saw SGD working well, and then you said, let me kind of bolster the properties of SGD, and I come up with new algorithms that are better than SGD. Yes?
So in all the graphs that you show, the error plateaus for a bit and then sharply drops. Plateaus and drops.
Yes. So beautiful question. Typically, when people train neural networks, they decrease the learning rate, the step size, in steps. So Praneet mentioned that the step size needs to go down as 1 over square root t. Typically, people fix it for a few epochs and then drop it, and then fix it for a few more epochs and then drop it. And you will see these training curves. In practice, you don't get good answers by dropping learning rates as 1 over square root t or 1 over t. This typically works much better for generalization. We don't really know the reason why yet, and there are many people working on this as to why this specific style of dropping works better than what optimization theory suggests. Yes?
Is this kind of phenomena present in image data sets, or have you also
No, so I've also seen the same in text. Any more questions? Okay, so let's come back to the main question. So we can come up with better versions of SGD, but why does SGD work so well in the first place? So these better versions are also more complicated, right? So let's try to see what makes SGD tick. And there are 2 players in this game. One of them is what is called the diffusion matrix. It is the variance of your stochastic gradients. So your gradients are stochastic. The stochasticity lies in the mini batches, and I'm going to compute the variance of the gradients. Turns out this variance is some matrix D. The size of D is again number of weights times number of weights, and then it goes down as 1 over batch size if you're sampling with replacement your mini batch. As the batch size goes to infinity, the variance goes to 0. Okay. The second player is what you might be more familiar with, called temperature. I'm going to call my temperature beta inverse, which is the ratio of the learning rate and the batch size. Larger the batch size, smaller the temperature, larger the learning rate, larger the temperature. Okay. You can now write down a more accurate model for SGD. So SGD takes a mini batch and then computes the weight update on this mini batch. We are going to write it down as a stochastic differential equation, where again the incremental change of your weights, dx, is given by the full gradient, which is the drift term, negative gradient of f, plus some Brownian motion. This Brownian motion is now dependent on what location you are sitting at. So d of x is the variance of your stochastic gradients, and the noise has that variance. So this is a more richer model than we talked about when we talked about controlled stochastic gradient descent. What I would like to do is understand the solutions of this SGD. Why? Because in a non-convex world, it doesn't make very much sense to tell me that I'm converging to a critical point this fast, because there are many critical points. I'm going to fall into the first ditch that I encounter, and then the game ends there, right? You can't make any more statements. This is a more formal point of view, less useful perhaps, which says that I'm going to wait for time equal to infinity, let my Markov chain mix, let my SD mix, and if things are ergodic, etc., I can try to characterize what kind of solutions SGD reaches if I wait for long enough. Okay, a totally different way of looking at things. Both have their own merits, but this is the SD version. How do you understand the solutions of this SD? Well, you look at the corresponding Fokker-Planck equation. You might know this as the master equation. The Fokker-Planck equation is a sum of two terms. So the rho here is a distribution on the weights. It is a probability distribution on the weights. You can normalize it. The rate at which it flows, so the partial derivative of this distribution, you can start this distribution with a Dirac delta, which is how you typically train a neural network. And rho sub t is the partial derivative of this distribution with time. This is given by the divergence of grad f times rho, which is called the drift term. It tells you how you would flow if you had no stochasticity. And then a second term, which the heat equation had a Laplacian here. Instead of a Laplacian, you get you get something that is the divergence of d times rho. And this is what makes this equation much harder, because the Laplacian really depends on d itself. Laplacian is also the diffusion properties of this PD are dependent on what location you're evaluating rho at. Okay, evaluating rho t at. But nevertheless, we are interested in finding solutions of this equation. Let's simplify it. Let's look at the heat equation, which is simply divergence of identity, where d is identity times gradient of rho. Okay. You might have heard of this result that says the heat equation performs steepest descent on the Dirichlet energy. So if I start Brownian motion at this location, it likes to spread around in the entire room. Well, spreading around simply means that you're minimizing integral over all your domain omega of the norm of your gradient of rho. The gradient would like to be as small as possible. This is what happens in Euclidean space. And probably among the most beautiful results I have read in the past few years is the following. So the exact same PD, heat equation, can be seen as steepest descent in the Wasserstein metric on entropy, on negative entropy. Negative entropy is simply the integral of logarithm of rho, d rho. And what this means more precisely is instead of doing gradient descent in Euclidean space, in Euclidean norm on the Dirichlet energy, you're doing gradient descent in the Wasserstein norm on the entropy. I am a control theorist by training, so I like to think of these things as Lyapunov equations, Lyapunov functions. You can say the following. So the negative entropy is a Lyapunov function for Brownian motion. It decreases monotonically as I let Brownian motion flow. And these two things are completely equivalent. You can think of life in terms of your Euclidean norm, where you get the Dirichlet energy, or you can think in terms of the Wasserstein norm, in which you're living with entropy. What happens if you add drift? So now you have the heat equation term, the Laplacian, and you also have gradient of f times rho. So this is still a nice PDE. Turns out this has a famous name. So the functional that it minimizes monotonically, again in the Wasserstein norm, is what is called the JKO functional, Jordan-Kindle-Euler auto functional. And just as you had negative entropy for the heat equation, you have a second term, which I will call the energetic term. This term is the average of f of x, where x are drawn from your probability distribution rho. You're now minimizing a sum of your energetic term and an entropic term. This is pretty standard, so you will see things that are related to Helmholtz free energy in this formula. But this is a fantastic result, because now you know what is the function variational formulation for SGD. SGD did not have a variational formulation before. This is the loss function that is minimized by the distribution of SGD. Monotonically is the key point. Okay, so rho SS is the steady state. It may occur at time equal to infinity. We do not know. It depends on the mixing properties of SGD and the loss function f of x. The formal result that JKO had was Fokker-Planck equation is the steepest descent on the JKO function, this function in the Wasserstein metric. Okay, also done nothing new that we have done yet. Here is what happens if D is not identity. Now you have a drift term that is the same as the JKO functional, but then you also have like a more complicated Laplacian term. Turns out the Fokker-Planck equation still monotonically minimizes a free energy, but this free energy is very interesting. So by changing the noise, by letting D to not be identity, you haven't changed the entropic term. What you actually have changed is the energetic term. The energetic term is something that is the average of a function phi of x over your distribution. And I want you to focus on one point here. So you were doing SGD with loss function f. So you're taking your updates using the gradient of the loss function f, and this f does not show up in this formula. So because of this noise d, you end up minimizing some functional which does not depend on f. Of course, it's not true that it does not depend on f. Phi equals f if and only if d is identity. So if and only if your noise is exactly identity, then this will look like the JQ functional. As soon as it is not identity, you're minimizing some other functional than the one that you use to take your mini batch updates. And that's kind of a very drastic result, right? I gave you a loss function, you started training your network using this loss function, but because of the special noise properties that you got while doing SGD, you end up minimizing some other function. The critical points are different. And we'll kind of talk about this in the next slide also. So hold that thought. You can rewrite this free energy as the KL divergence between rho, which is a current distribution at time t, and the steady state rho SS, whatever you converge to, okay? And written in this form, it is very intuitive. So if you are doing convex optimization like the previous lecture, and I told you that you're minimizing your current location x minus x star, the distance to the optimal x, and you're like, of course, I mean, this is what I wanted to do anyway, right? This is the job of optimization. If not this, well, then what? Well, the point is you're also minimizing a similar quantity except in the variational world, and you're doing it monotonically. So just as in gradient descent, the distance between x and x star decreases monotonically, in SGD, the distance between not x and x star, but rho and rho star or rho and rho SS decreases monotonically. So everything remains the same. Acceleration also works. Everything works in the variational sense. Okay. Formally, it looks as follows. So the functional KL between rho and rho SS is minimized monotonically by the Fokker-Planck equation corresponding to SGD, and phi is exactly the log density of log steady state density. If your D is identity, then phi will be equal to F, because rho SS will be exactly be equal to e to the negative f of x, the Gibbs distribution. After writing down this formula, you can get like a few very straightforward implications. So remember that there is a beta here, and beta inverse was the ratio of the learning rate and the batch size. If you want a good beta, if you want a good regularizer in addition to minimizing the average energetic term, then you don't want beta inverse to be very small. That means that eta divided by beta divided by b should not be too small. And this is exactly what people noticed when they tried to train neural networks with very large batch sizes, that they had to tune the learning rate to scale linearly with the batch size. This essentially means that the temperature that you're looking at while looking for generalization results should not be too small. Okay? If you sample your mini batches without replacement, then you get a term which is your original beta, the one with that you got for sampling with replacement, times 1 minus b over n, where n is the number of data that you have. And as you can see, this term goes to 0 as you keep increasing b closer and closer to n. And you notice this if you train with very large batch sizes without replacement, and you get this kind of trivially by writing down the variational form of SGD. Okay.
But then sometimes some of the schemes are with replacement, but organized.
Yes, so typically every epoch you would shuffle the data, and then yes, so that is not in this model because this is like a much more formal model than shuffling the data at each epoch. There are no epochs here.
This remark goes in that direction.
Yes, yeah, yeah. I want to kind of connect to another thing, what is called the information bottleneck principle. So Naftali Teshby is a famous physicist also in the world of neural networks in the late 80s or the late 90s. And he came up with the following idea. So if I have data X, I would like to make certain predictions from this data. Let's call them Y. I'm going to create another random variable, let's call it Z, from this data, which I would like to think of as a representation of my data or a statistic of my data. What are good statistics? Good statistics are those that do not throw away a lot of information about my data. I can reconstruct the data easily using the statistics. So this is what would be the perspective of coding theory. You take your data, code it up into some other space, and then this is a good code if you can reconstruct your data back. In machine learning, you're not interested in reconstructing the data. You're interested in making predictions on why. So what are good statistics? Good statistics are those that throw away information that is not relevant to these predictions. You show me a lot of pictures of dogs on grass, I should be throwing away the grass. I should not be letting grass inform my decision about how likely this image is that of a dog. Okay? So this is what is called the information bottleneck. You're minimizing the information that goes into your representation Z that is not relevant to your task Y. And typically when people try to instantiate these ideas, they'll come up with loss functions of the following form. So you might have seen this by many different names. One of them is called the evidence lower bound. And here's how it goes. So I would like to come up with a distribution on my parameters. I call it rho theta in this case. The density is parameterized by theta. It minimizes the average loss. That is an easy thing to think about. I would like my neural network to do well on my loss function. And I'm going to regularize it using some scale divergence term. This scale divergence is the distance of my variation distribution rho theta with respect to some prior, a prior of my choosing. Okay, this could be a Gaussian prior. Typically, people use mean field priors, etc. You will also see very, very similar functionals when you do what is called pack-based theory. And the name of the game is I should be minimizing this function instead of simply the first term because I get a regularizer that I can control with. Okay. It's not very easy to minimize these things because it's very hard to pick a prior which lets you take the gradients easily, and that is why we are stuck with mean field priors. And every time you kind of write down a loss function like this and minimize this using SGD, SGD implicitly enforces a uniform prior on your weights because we saw that this term was entropy. The entropy is the scale divergence between your distribution rho and a uniform distribution on, let's say, some bounded weight space. So SGD secretly is enforcing a uniform prior. You, on the other side, are enforcing some other prior, and now you get into a fight with SGD, which you don't even know about. So this is happening under the hood when you take gradients of the first term. And that is why people have kind of played a lot with this constant that they like to put in front of the KL as beta VAs, et cetera, But the crux of the matter is that SGD wants one prior, a uniform prior, which is good for certain special reasons. You want some other prior because you are looking at the data as a scientist. And you don't know good ways of controlling this fight. You should kind of try to imagine the following scenario. So understand the prior that SGD enforces and then only modify the prior if you need to. So SGD minimizes some form of this functional naturally. If you don't respect it, then you won't get good answers. That is why these Lagrangians have not shown good generalization results. They typically are written down as formal equations or formal calculations, but they don't give you state-of-the-art generalization performance. We'll kind of breeze through this a little bit. Pretty sure I don't have 30 minutes left. When am I supposed to end? Okay. This I alluded to in a bit. Your function phi that SGD minimizes is equal to f of x if and only if noise is identity. If they are different otherwise. And for neural networks, they are not at all. It is not at all identity. In fact, the rank of D for a typical neural network is as small as 0.5%. Think about this. So you have 1 million weights in your neural network. Your stochasticity, which is given by the rank of D, lies in a subspace that is as small as 0.5%. Everything else is just gradient dynamics. These are exactly the directions in which gradients of different images do not like each other. And they interfere with each other. This is the eigenspectrum again of the matrix D that you can evaluate using one epoch on your data set. Yes. Okay, thanks. And what you'll notice is that the rank is so small. So SGD for neural networks is doing something that is very, very out of ordinary. The noise in SGD is highly degenerate. It only lets you move in certain special directions. So for the physicists in the room, this is a Markov chain with broken detailed balance. There are some directions that that SGD likes, and then you don't get to come back with the same probability in some other directions. There are some implications of this result for architecture search, in the sense that architectures which have these properties are good, architectures which do not have these properties may not be good. The fact that D is low rank. Because if D is full rank, then it's somehow a much larger space that it has to travel to. So the complexity of the hypothesis class is much larger. What this really is saying is that even if your hypothesis class is larger on paper, SGD doesn't let you see all of it. It lets you only are restricted to a small subspace. Yes.
Driving the noise is in fact low rank, not full rank.
Mm-hmm.
So it's not analytic in SD.
It is not, yeah.
Is it hypoelectric? Do you have the existence with density?
I don't know. So in this paper, yeah. So I'm using, yeah. Yes. So we assume that the density exists. We assume that ergodicity is not broken.
No, but for the existence of density, when you have a D which has small rank,
Mm-hmm.
it's hard to get. You need
Yes.
some bracket generating.
Yes. So I don't know. Pretty sure, yeah. So
Your measure will be carried by some kind of integral leaf. I mean, something smaller dimension.
yes, yeah. So we don't know good ways to say that the density exists. It should exist, right? I mean, things shouldn't be that bad, is what I would expect. But yeah, I don't have a better answer.
In fact, that's a question that is approachable. If you can look to the brackets of the columns, the Lie bracket of the columns.
Of the T. So we have a new paper which kind of analyzes D better. We kind of used like a connection with an ODE. It's like an ODE living on a manifold, and the manifold's metric is exactly D. So it's a sub-Riemannian manifold with an ODE living on it. Okay, so some intuition as to why this occurs. This occurs because images are not that different. They're coming from the same world. If I give you a white dog and a white cat, essentially most of the pixels are white fur. So your gradient will differ only in places where they are different, and most of the neurons will get the same gradient. And this is why you have D that is so degenerate. But this is not a pathology, right? So it is a fundamental fact about the data. It is also, in fact, a fact about architecture. So deep architectures have symmetries. If you imagine matrix factorization, if I want to write down a matrix X as a product of two matrices A and B would be the weights of my two layers, and X is, let's say, an autoencoder. Then all solutions A times P, where P is an invertible matrix, are also good enough solutions. They have the exact same input-output loss function, and these are what are called symmetries in the architecture. As soon as you have a hierarchical architecture, you have symmetries, and you will lose the rank in D, because all the neurons are not independent of each other anymore. So two causes, some of which we are close to analyzing in recent papers. I'll kind of, maybe I'll do this, yes. So now we talked about what is the distribution on the weight space induced by SGD. What are the trajectories of SGD like? The trajectories of SGD, as you can imagine, are a little pathological because the noise is so special. What you can write down is you can essentially take your original gradient field, gradient of F. You can remove some conservative term from it, which is D times, which is the divergence of D. And what you're left with is a J. A J is what is called a non-conservative force. So it doesn't come from a potential. And the most likely trajectories of SGD are not balls that bounce around in local minima, as you would expect. They are essentially limit cycles or closed loops in the parameter space, where you can use gradient dynamics to travel without any problems. So this is essentially a complete artifact of D being degenerate. Okay. you can also see these things in experiments. So this is an experiment where I took a small neural network on MNIST and I ran it for 100,000 epochs. And I'm trying to draw the fast Fourier transform of the successive weight updates, of the incremental weight updates across these epochs. What you can see is there is a large, at small frequencies, there are periodic components with a large amplitude. And then this is another part of the spectrum that we only know very briefly about. At high frequencies, the amplitude again increases. But broadly speaking, there are periodic components in these long trajectories of SGD. And these periodic components are exactly the ones that are coming up because your noise is degenerate, because your SGD is essentially some deterministic dynamics with very minor amounts of noise added around it. Let's skip this. To close, I want to say the following. So when you do machine learning, let's say you are training an SVM, you cook up a kernel, you don't worry about optimization. So I wonder how many of you know what algorithm scikit-learn uses to minimize an SVM. It's in a case, it's LBFGS. But so you don't worry about optimization. You train it, you give it to some closed form solver or some nice solver. And when you get generalization, let's say you get a bad generalization, you immediately go back to the architecture to pick a different kernel. You never mistrust optimization. In deep learning, this thing does not seem to be true. So the architecture that you pick fundamentally changes the optimization. The optimization that you pick fundamentally changes the generalization. So all these things are completely entangled together. And that is why understanding deep learning is so hard. I believe that is also why deep learning is powerful, because all these things are connected to each other. They're not independent of each other. And if you really wanted to get a crisper understanding of these three different phenomena, what architecture should I pick? How should I train it? And what generalization error do I expect? What should I do if I want to improve my generalization error? Then what you really need to do is understand how real data plays into this game. So when you do learning theory, be it VC bounds or be it tag-based bounds, you take the data and throw it out of the window. You never ever make models of your data. You never understand how data informs training. And the diffusion matrix D is an example of a quantity that you can evaluate on your computer right now, on your laptop, that tells you something about what real data looks like. So you don't care in deep learning, or you may not be able to access very crisp convergence results in deep learning, but what you can get are laws. So long as my diffusion matrix has so-and-so property, then I can go off and build a little theory on top of that. This is, I am building a theory on empirically measurable quantities. I need not know why they are the way they are, but so long as they are like this, I might be able to explain a majority of the practice around them. So this is how I believe we should be approaching theory for neural networks. Try to come up with at least some rudimentary principles that give you bulletproof training, bulletproof predictions, and then you can kind of work to make them crisper, like we do in optimization or like we do in statistical learning theory. And data seems to be at the key, at the crux of it. We haven't started playing with data yet in machine learning, theoretically. I'll not worry about this. I'll conclude here. And the papers that I talked about are on my website, and questions if you have. Thank you.